Hello again. This is Math 2134 coming to you from the College of DuPage, and the title of this lecture is Numerical Integration. And as always, please be an active learner as you watch this video. By way of introduction, in many situations it may be difficult or impossible to evaluate a definite integral using an antiderivative. Sometimes you don't know how to find it, and sometimes it even can't be found. To address this difficulty, we developed ways to approximate the value of a definite integral using geometry, a process called numerical integration. And two common situations can occur that require the use of numerical integration: when you cannot find, or it's impossible to find, an antiderivative, and here's an example that comes from statistics, or when the data may not be easily modeled by a continuous function. So let's begin by talking about a situation where the data consists of individual points. We will discover that it's not necessary to find a continuous function that models the data. So here is some data, and this is the calories burned per hour during a workout, and the time is shown in 30-second intervals from 0 to 10, and that's 30-second intervals. And these are the measures of the calories that are being burned at 1, 2, 3, 4, 5, and this apparently is a variable intensity kind of thing, and you have all of these data points. Well, what you do is what we did earlier, is you connect the dots, and in this case we're using the left endpoint, and we're creating, and all of these down here are 30-second intervals, so the base of all these rectangles are 1/2 minute or 30-second intervals, but the height of these are going to be, and we'll always take the left endpoint, and so we take the left endpoints and build rectangles, and we can figure out the area of the rectangles. These were the things we called Riemann sums before, and we'll call them Riemann sums again. So you see, 30 seconds is 1/120 hours, so the width is always this, and on the subinterval we're always taking the left endpoint, and so we're taking 0, 1, 2, 3, and so on and so forth down to 9, and then we're reading these values off the graph. We're multiplying calories per hour times hours, and we're getting calories for each of those rectangles, and we can add them together and find out that the total calories burned in this workout of 5 minutes is around 10.416 calories. Again, we've done this before. Now we also could draw rectangles using the same data from the right endpoints, and we get a slightly different answer. Here we get 10.625 calories. But again, it approximates the area under this curve, whatever the curve actually happens to be. And the calculation is much the same. So we have this definition again of Riemann sums. So let the closed interval AB be subdivided into n equal subintervals. A to x1, x1 to x2, x2 to x3, all the way down to xn minus 1 to b. And each width is a common width. It's the total length, b minus a, divided by how many subintervals, n. And we assume that f is defined for all of those points. Then the approximate value of the definite integral from a to b of f of x dx is given by L, and this time we're calling this L sub n, and we are using the left endpoints again, where L sub n is equal to, and so the height of these are going to be these values. The width of the intervals is b minus a over n, and so the approximate value is given by r sub n, which is this same value, except what we're doing is we're counting this one to be the first one, and this to be the n minus 1 one, and we're inserting b minus a into that. Okay, so let's talk about using this for a problem. So here you have Ken, who rides his bicycle for 10 minutes, and the table below shows his speed, v of t, in miles per hour. So you see this table just gives you some points. So this is t, this is v of t. Now t is in minutes, it's important to realize that, and v of t is in miles per hour. And so what you want to do is, for each 1 minute interval, and that data shows us for each 1 minute interval, we want to find L10 to approximate the total distance he travels. You see the area under a velocity versus time curve is velocity times time, which is distance. Okay, so for the units then, the width of each of those rectangles is going to be 1 minute, or 1/60th hour. We have the data for how tall they are in miles per hour. If I take the product of miles per hour times hours, I get miles. I do all of those calculations. I would encourage students to actually verify these calculations, but then you would find how far does Ken travel, and Ken travels approximately 2.449 miles. Now the same approach can be used in a situation where we have a function that we don't know how to find the antiderivative, and here's an example. So suppose we took a function f of x equal the square root of 1 minus x cubed. We can't find an antiderivative of this with the techniques we've learned so far, and so what we want to do is we're going to use a Riemann sum to estimate this. Now you see what we can do then is we can think about the graph of the function, which is shown in red here. And we can pick some endpoints, and we're picking endpoints here. Let's see, it's going to be 1, 2, 3, 4, 5, 6 intervals, and so we're doing this for 6 intervals. And the width of each of those intervals, you see we're going from 0 to 3, so each of those 6 is going to be 1/2 in length. So you see the width is always going to be 1/2. The left endpoint, we just plug it into this function to figure out what the left endpoint is approximately. And the area then is going to be, in each of the rectangles, is going to be these numbers, and I add them up. And when I do that, I will end up with that this definite integral from 0 to 3 of the square root of 1 plus x cubed dx is approximately equal to, and I did it here using the left endpoint, I did it here using the right endpoint, and I just took the average of the two, just to make it a better approximation, is 7.396. We don't have to use the left or right endpoint. We can also use the midpoint. Here's the midpoint rule. Let the closed interval AB be subdivided into n equal subintervals with width delta x equal b minus a over n, and assume that f is defined for each of these midpoints of the subintervals that we get this way. Then the approximate value of the definite integral from a to b f of x dx is given by m sub n, that's the midpoint rule using n divisions, is going to be b minus a over n, that's the length of the interval, times the height. And in this case, we're taking the height of the rectangle to be the value of the function at the midpoints. And then we add up the areas of all of the rectangles. So let's find, and this is the same thing we were doing before, the integral from 0 to 3, the square root of 1 plus x cubed dx. This is the same example, but now we're using the midpoint rule. So the only thing that really changes here is that we are going to be talking about the midpoints. And let's see, this time we're using 6 subintervals, 1, 2, 3, 4, 5, 6. And so we'll find out what the midpoint is. The width is still this. We put the midpoint into the function to figure out the height. We take the height times the width, and we get these numbers. We add them up, and this time we get that the area using this midpoint rule is also close to the same thing, is approximately 7.315, and this compares well with the other examples we found using the left and right end points. Now, we can use other geometric figures than rectangles to do this, and one popular kind of figure is called a trapezoid. Now, this little first box here is a trapezoid because this side is parallel to this side. This is one base of the trapezoid, this is the other, and so those are parallel, but then this is a side of the trapezoid, and this is the other side of the trapezoid. And so you see the trapezoid means what we're doing is we're connecting the points that we're picking, and we're using straight lines. So these are going to be adding up the areas of the trapezoids that we have. Now, when you think about the first trapezoid and the second trapezoid, it has this point in common. So you realize that that point is somehow going to get counted twice in the calculation. So the first trapezoid has width delta x, that's the change in x down here, and heights f0 of x and f1 of x. So the first trapezoid's area is this, the average of the bases times delta x, or the sum of the bases divided by 2 times delta x. The second trapezoid is this, f of x1 plus f of x2 over 2 times delta x, and so on. Now, when we add these together, then, we say that the definite integral from a to b f of x dx is approximately equal to the area of those trapezoids. But notice that fx1 over 2 and fx1 over 2 happen twice, and many of these happen twice, and so we have to factor that in. But what we can do is we can factor out delta x from that, and we get this expression, but this one and this one add together, so that's really just going to be f of x1, this one will be f of x2, and so on. So we have the final result, that the definite integral from a to b of delta x times, and this is what we get. And putting it in a box, this is the general approach. Let the closed interval AB be subdivided into n equal subintervals, and the widths are common. It is delta x is equal to b minus a over n. And we assume that f is defined for a, x1, x2, all the way up to b. So the approximate value of the interval is given by t sub n. And t sub n is equal to b minus a over n times, and this is the expression that we have. This is very easy to compute, and that's another thing that is very attractive about this. In fact, this is easier to compute than the other approaches that we've talked about so far. So let's do an example. Let's use the trapezoidal rule to find T4. Now T4 means we have 4 trapezoids. 1, 2, 3, 4. And we're approximating the definite integral from 1 to 3 of the cube root of x plus x to the 6th. Now, this again is an integral that you cannot do by substitution, and so this numerical integration is very appropriate. So we divide this interval from 1 to 3, which is of length 2, into 4 subintervals, and each of those is of length 1/2. So T4 by the formula is going to be 1/2, and we plug in all of those values. Plugging in those values and doing the calculation using our calculator, this is approximately equal to 8.897. There's another geometry that is often used, and this involves Simpson's rule. So we have a red function that we want to estimate the area from A to B under that curve. But instead of drawing lines in between consecutive points and use trapezoids, here we say let's take 3 points, and with 3 points we will put a blue curve through those, and the blue curve is a parabolic arc. Now there's a lot of computations that are involved with this, but the formula that we get at the end is really quite simple. So what we do is we take this interval and we divide it into two equal subintervals, and a plus b over 2 is the midpoint. And so we have three values, and so what we can do is we can calculate the area under the parabola. And by the way, we know how to find the area under a parabola, and in fact we do that formula here. So this integral is approximately equal to b minus a over 3n times the area of that parabola. And this could be an exercise that you could do. Now let's extend that to have more subdivisions. Now if n is even, then n over 2 is a whole number and represents the number of parabolas. So we do have to have n to be even to use this approach. That is not a difficult problem. And again, we use 3 to estimate that with a parabola. We use the next 3 to estimate it with a different parabola, and so on. Kind of involved in theory, but the final formula is simple also, remarkably simple. So it's called Simpson's rule. Let the closed interval AB be subdivided into an even number n of subintervals with width delta x equal b minus a over n, and assume that f is defined at all of those points that we divided into. Then the approximate value of the definite integral from a to b f of x dx is given by script s sub n, or capital S sub n, where capital S sub n is b minus a all over 3n, and these are going to be the values that we take. And notice there's a pattern: 1, 4, 2, 4, 2, 4, 2, 4, 2, dot, 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 2, 4, and 1 again. And so there's a definite pattern. This is very easy to program and use. So it's very satisfying that way. Let's use this with an example. And here we're going to find S2 and S4 approximations of the definite integral from 0 to 2 of the square root of 9 minus x squared dx. So for S2, we divide 0 to 2 into two equal parts, this one and this one. And we're going to use the formula. So the formula is S2 is equal to, we substitute those values, and when we're substituting these values for f, we substitute into f, which is the integrand. We do the calculation and we get this as 5.516 rounded. Now for S4, we divide it into four subintervals. Again, we use the formula and we substitute in and we get this. Notice there's not a whole lot of difference between these two. So both S2 and S4 are what turns out to be very accurate approximations for this, because this is the exact answer. I shouldn't say exact. This is the approximate answer to 4 decimal places, and you can see you get really quite close to it with these not n being too big of a number. That's very satisfying. And in fact, there is an important theorem that is beyond the scope of this course, but you should know that this exists because you can use it. So suppose the second derivative is bounded above by a number k, and the fourth derivative is also bounded above by a number m, and this is the absolute value of those derivatives. So there's a lower bound and an upper bound for those functions in between a and b. Then if e sub m, standing for the error, E-R-R-O-R, and using the midpoint formula, E sub t is the error that you would encounter using the trapezoidal rule, and E sub s are the errors associated with using Simpson's rule. You have the following bounds. So the absolute value of E sub m is less than or equal to this expression. The absolute value of E sub t is less than or equal to this expression. And the absolute value of E sub s is less than or equal to this expression. Now, so the bigger you make n, the tighter your estimate can be. And from this you see that Simpson's rule is a sharper estimate generally. As you can see, this theorem enables you to write a computer program or use a standardly available computer utility to estimate any definite integral satisfying those hypotheses. These are the hypotheses up here. to any desired level of accuracy. You just pick n to make this number less than whatever accuracy you want. Said another way, if you know how accurate you need to be, you know how big to make n. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.